Okay, so today we're going to look at something that's called Euler's method. The fact of the matter is many ordinary differential equations, ODEs, do not have an analytic solution. Like you can't write out an equation that is its solution. But Euler's method allows us to estimate a particular value for a solution for an ODE initial value problem. So let's first describe the method and then we'll see how it works. Okay, so you have sum f prime of x, y is equal to dy dx when at the point x, y. Okay, so what we're going to do is we're going to let x null be equal to the starting point. We're going to let y null be equal to its starting point. And then we're going to let the nth x be equal to x null plus n times h, and yn be equal to yn minus 1 plus h times f prime of x at n minus 1 and f prime of y at n minus 1. So let's clean that up a little bit. It's kind of messy. F prime of x at n minus 1 and y at n minus 1. All right, so this is an iterative process, and h is going to be a step size that is going to be given for the problem. And the smaller the step size, the more steps that you'll have to take to find a solution, but the more accurate your solution will be. So let's take a look at a specific example of this and see if we can't make some sense about what we're talking about here. So let's say we want to find a solution for the ordinary differential equation dy dx when where y equals 1 when x equals 1. And we're going to use this to find an estimate for the solution when x is equal to 1.4 using a step size of 0.1. All right, so my initial value, x0 is my initial value, so that's 1. My initial value for y is also 1. All right, so x1 is going to be 1 plus h, so that's going to be 1.1. And y1 is going to be y0, which is 1, plus h, 0.1, times f of x0 times y0, so that's going to be 1 times 1. So this reduces, let's see, 0.1 times 1.1, or 1 times 1, right? 0 says it's going to be 1 times 0.1, so it's going to come out as 1.1. All right, so, all right, we've gotten the x value, an estimate for the x value at 1.1. So we're going to take another step. We're going to go to 1.2. So y2 is now the last value, 1.1, plus the step size, plus the derivative at the previous x value and y value. So let's see, the previous x value is 1.1. The previous y value is 1.1. So we're going to multiply those together. See, 1.1 times 1.1 plus 1.1 is going to give me 1/10 plus 1.1 is going to give me 1.221. Okay, so we've kind of moved again. So we're getting closer to 1.4 here, and we're tracking the y value along the way. All right, so let's try x3. So x3 is now 1.3, y3 should be this 1.221 plus the h value, right? And now my derivative. So the x value of the derivative is 1.2. The y value of the previous term is 1.221. And we do that computation, and we're going to end up with 1.36752. Okay, so we're almost there. Let's try it one more time. If we make x4 1.4, this means y4 is going to be 1.36752 plus 0.1. And then we take the x and y values of the previous iteration, so that's 1.3 times 1.36752. If you do that calculation, you end up with 1.5452976. Okay, so what have we just done? We've basically said that if my solution goes through the point 1, 1, and it has to have this derivative, then I've estimated that its y value when x is 1.4 is approximately 1.55, somewhere around there, or 1.545. All right, so why does this work? All right, so if I kind of like build a graph of what's going on here, we find my initial value. My initial value here was at 1, 1. So this is like I'm on the slope field, and I just put the little kid down on the tricycle, and the derivative is going to tell me which way he should go. So my derivative at the point 1, 1 is 1, right? So we're going to go out here from 1 to 1.1, and at 1.1 he raises to 1.1. So my little kid goes there. He's followed the path. Now, basically continuing to drive on the slope field at 1.1, right? I'm now going up to 1.2, right? So when I took the second step, he went up to like 1.221, so slightly more than 1.2. So I'm curving a little bit more upward. And then at 1.3, we went up to like 1.36, right? 36. So 1.36 is between like 1.3 and 1.4, about halfway. So it went up this way, and maybe not far enough over. 1.3 is here, right? So about 1 point. There we go. 1.3.5. There it is. Okay, so we got there. And then finally at 1.44, we're way up here at like 1.545. So there's 1.5, 1.6, kind of up a ways here at 1.4, and there we go. So though we're making straight line approximations after straight line approximation, after straight line approximation, after straight line approximation, you can see that this is starting to approximate a curve, and that curve would be the solution that my little kid would follow on the tricycle by starting here and following along on the slope field. Okay, so this value here, where I have 1.4, comma 1.545, is the correct location of that point. And, well, it's not necessarily exact, right? It's going to be off by a little estimate. But ultimately, this is saying that if I were to solve the ODE with this initial value, then 1.4 should be attached to the curve around 1.545. It's a pretty good approximation. If you actually do a little bit of the work on this, we're going to show you that this particular differential equation actually has an analytic solution, and we'll compare our result to the result from that solution. Okay, so my argument here is that y equals e to the x squared minus 1 over 2 is actually a solution for this differential equation dy dx equals that xy at the point that goes to the initial value x1, y1. How do I know this? Well, the first thing to check is to see if the initial value actually goes through this. So let's put in 1 for x. That's e to the 1 squared minus 1 over 2, which is e to the 0 over 2, which is e to the 0, which is 1, which means that when I put in x as 1, I get out y as 1. So the point 1, 1 is in fact on this curve. Now the question is does this curve satisfy this derivative? So let's see. If I take dy dx, well, this is going to be e to the x squared minus 1 over 2 times the derivative of the inside, which is what we got, 1/2 times 2x, right? So that's just e to the x squared minus 1 over 2 times x. But this, if you look, is y. So this is y times x, which happens to be equal to x times y, which is what we want to prove that the derivative is equal to. The derivative is equal to x times y. So ultimately, my derivative solves the differential equation, and it goes through the specific initial value, x1, y1. So we are good to say that this is the analytic solution to this ODE, an initial value problem. So let's see what happens. If I find y when x is 1.4 using the actual analytic solution, I get e to the 1.4 squared minus 1 over 2, which works out to be e to the 0.48, which is approximately 1.616. Now, if I take that and I compare it to the 1.545 that came out when I did the original analysis, using Euler's rule or Euler's method, the relative error here is 4.4%, which isn't bad. I mean, like 95% to the good is usually a pretty good estimate. How do we make it better? Well, you would make your estimate better by using a smaller step size and more steps. Now, I'm not going to work all of that out, but I will show this, that if you did this with 8 steps instead of 4, you would end up with 1.57868825, and your relative error would drop to 2.3%. So Euler's method with more steps is actually going to cause your relative error to drop every time you add more steps into the process. Now, adding more steps causes you to have more computational cost, but you'll gain accuracy with that process. So let's do a second problem with Euler's method and see if we can't get some procedure on. Okay, so let's get a different differential equation. Let's say dy dx is equal to x plus 2y, and the initial value here is going to be when x is 1, y is 0. Okay, we're going to do this with 4 steps. So h is going to be my step size. We're going to look for a solution for when is x2, right? So that's what we want. We want the y when x is 2. So h is going to be 1/4 is my step size, or we can use that as 0.25. So let's start the game here. The initial value is x0 is 1. y0 is 0. All right, so the first step is going to be 1/4 of the way to 2, so it's going to be 1.25, right? So y1 takes the previous y value plus the size of the step, 0.25, times the derivative, at the previous point, so it's going to be 1 plus 2 times 0. And let's see, that's 0 plus 0.25 times 1 makes my new value 0.25. Okay, so let's take the next step. Let's go, x2 is now another quarter of a step, so that's 1.5. All right, so y2 is going to take that 0.25 plus the 0.25 step size. And let's see, the previous x is 1.25. We're going to that to 2 times the previous y is 0.25. Right? And if I work that out, I'm going to end up with 0.6875. So let's see, x3 now puts me at 1.75. y3 starts me at 0.875 plus the step size, 0.25, times the derivative, which is going to be the past x, 1.5, plus 2 times the past y, 2 times 0.06875, which lands me at 1.40625. Okay, so let's do x4. x4 is finally at 2.0. y4 takes the last y, 1.40625, adds the previous step size, 0.25, times, let's see, the previous x is 1.75, plus 2 times the previous y, 1.40625. And if I do that calculation, x4 comes up as 2.546875. So 2.546875. Okay, so what is this telling me? This is telling me that if this is my ordinary differential equation, and this is my initial value, 1, 0, and I follow Euler's method with a step size of 0.25 until I get to 2, then I get an estimate that says I'm approximately 2.47 or 2.547, or 2.547 is an approximate answer to, or approximate value for the solution to this ordinary differential equation at this initial value. So this is my value for x equals 2 for this ODE at this initial value. All right, so Euler's method is used to solve an ODE initial value problem for a particular value, and we've given you a couple of examples of it, and we will work some more of them in class. Thank you.